Okay, so on behalf of our presenters, I just wanted to say thank you for attending, and we really appreciate your attendance, and we hope that everyone is staying safe and healthy. Before we get started, I just wanted to take a minute to walk through a couple of WebEx functions and to cover our Q&A process. All participants are muted to reduce background noise, echoes, or feedback. We do ask that you remain muted for the whole webinar. To be respectful of everyone's time and to keep this webinar to the hour allotted, we've planned a Q&A session at the end of the presentation. We ask that you send any questions throughout the webinar as a chat, and we will do our best to answer those live. If you've only dialed in through audio, in order to ask questions and to use the chat, you'll need to join the webinar through the WebEx link that has been sent to you via email. To send a question with chat, simply hover over your screen and you'll see the round button with a speech bubble. Click on that bubble and your chat panel will open. Type your question in and into the message box and press enter, and we'll do our best to answer any questions, but we can reach out after via email should we not be able to address your question. Okay, so that should cover any WebEx or Q&A concerns. I'm just going to say a couple quick words of introduction before we turn it over to our first presenter. So this webinar is on UK fire safety and external wall cladding by Jensen Hughes. Jensen Hughes are the global leader in fire safety, security, and risk-based engineering and consulting. We're a team of over 1,400 engineers, consultants, and scientists who develop and deliver innovative and cost-effective solutions to a global client base. Our speakers today are from Jensen Hughes' IFIC Forensics, JGA Fire Engineers, and experts from our fire testing group. IFIC Forensics was founded in 1970 and joined the Jensen Hughes family at the end of last year. It is a market-leading forensic investigation firm operating throughout the UK, Ireland, and overseas. It's comprised of highly experienced consultants committed to delivering technical excellence for clients across the full spectrum of services. JGA joined Jensen Hughes in 2018 and is a specialist fire engineering consultancy operating throughout the UK, Ireland, and internationally. JGA has 27 years experience and over 6,500 projects worldwide, providing safer and more efficient buildings. So our presenters today are as follows. Jim is a principal investigator at IFIC Forensics. Jim has conducted numerous fire investigations. His experience includes industrial, commercial, and residential fires and explosions. Ben Atkinson is the group technical director at JGA. Ben is responsible for leading projects worldwide and for the development of the fire strategies for a wide range of complex buildings. Art Parker is a senior fire protection engineer at Jensen Hughes, specializing in the testing and evaluation of all facets of fire resistance rated construction and materials flammability. And finally, Dan Martin is a fire protection engineer at Jensen Hughes. Dan provides consulting services related to passive fire protection schemes, standardized and non-standardized testing, building development, and fire investigation services. So in our session today, we're going to cover the review and history of cladding fires, present climate in the United Kingdom, testing best practices, and remedial EWS1 assessments with a Q&A period at the end. Okay, without further ado, I will pass it off to our first presenter. Jim?
Good afternoon, everybody. I'd like to review the history of cladding fires, and the history begins with a fire that occurred near IFIC's Glasgow office in Irvine. Can we have the next slide, please? This was at Garnet Court in Irvine in 1999, and you can see that a flat fire extended up the cladding to the top of the building. And this alerted the fire safety community of the dangers of fire spread vertically up cladding. Next slide. So what is aluminium composite cladding? Well, effectively, an aluminium sandwich with a plastic core. The sheets of aluminium are typically 0.5 millimetre thick, and the core, plastic core, is about 3 to 4 millimetres thick. This core has typically been made of polyethylene, which is highly flammable. Next slide. But it's a material that's loved by architects because it can be molded into various forms and produce attractive buildings, such as the one in the picture on the left here. Next slide. There have been many ACM fires over the years, and I've listed perhaps the most well-known of them. Next slide. The first occurred in 2009 in the Television Cultural Center in Beijing. And this is one building which is aflame. Next slide. And 5 years later, in 2014, there was a fire in the Lacrosse building in Melbourne. Again, rapid vertical spread and horizontal spread of this fire. Next slide. ACM was popular and is popular in Dubai, and there have been several ACM fires. The best known of them are the address fire, which occurred in 2016. Next slide. And there was a fire in the Torch building, which I'll illustrate in a minute. But this fire is interesting. It occurred in Singapore. Sadly, a lady was killed in the stairwell, which was open to the cladding. And quite how this fire originated is not known to me, but it spread very quickly up the external facade. Note the date, May the 4th, 2017. And the next slide shows the Grenfell fire, in which 72 people perished just 6 weeks after the fire in Togan Road in Singapore. Rapid vertical spread from the floor of origin to the top of the building within 20 minutes. And then the fire began to wrap itself round the building, having spread at the crown and spread downwards. Most unusual fire spread. Next slide. And then the fire at the Torch building. Again, this is another fire in Dubai, which IFIC investigated. Rapid spread from a balcony up the face of the building. But in the two fires at the address building and the Torch, there were no fatalities. But these were modern buildings with two stairwells, as opposed to Grenfell, which was a reclad of a building constructed in the 60s with a single stairwell. Next slide. We're also concerned with high pressure laminate fires, and there have been 3 fires of note within the UK. Next slide. At the Royal Marsden Hospital, which was well documented. There were TV crews there to record the spread up one of the towers of the hospital, and then the roof became engaged. Next slide. Better known, the fire at Lakanal House in 2009, which 6 people died. Interesting fire spread both vertically and vertically downwards in this case. And more recently, next slide, the fire at the Cube in Bolton. Next slide. These fires have caused a lot of research to be done, and this latest paper that came out in the early part of this year by McKenna et al. Compares the fire behavior of different types of modern facade materials, and I've summarized the results on the next slide. And what you will see is that the peak heat release rate of ACM and of HPL is 55 times and 25 times higher than the least flammable panels, and they release a lot more energy over a longer period of time. They also compared in their tests polyisocyanurate foam, PIR, and phenolic foam with the least flammable sorts of insulation, stone wool, rock wool. And you can see there that the total heat release rate from a polyisocyanurate foam is 35 times higher, and a phenolic foam even higher than that, 48 times. So there is a lot of energy contained and able to be released in a fire with these insulation materials. And one of the things that the researchers note is that a few burning drips of polyethylene from paneling are enough to ignite the foam insulation. And with that, I'll hand over to Ben, who's going to talk about the present climate in the UK. Ben.
Thank you, Jim. Before I get onto the present climate, it's probably worth a few slides which cover the climate prior to Grenfell, because I think that helps inform, perhaps helps inform how we got to where we are. So on the first slide, this is showing the trend in fire-related fatalities in England in the 15 or so years prior to Grenfell. The top line in the graph is showing fatalities in dwellings, which is where the vast majority of fire deaths occur. As you can see, the trend is broadly positive, from around 350 a year at the turn of the century to just over 200 in the years immediately before Grenfell. That also compares reasonably well internationally. This graph is showing data collected by fire brigades around the world. Now, international comparisons are very difficult, as we're constantly hearing about COVID at the moment, but it's equally true of fire statistics. Different countries collect data in different ways, so it's probably not a perfect comparison, but as far as it goes, it looks pretty good. Great Britain is down there in the bottom right at around about 0.5 fatalities per 100,000 inhabitants, and that compares pretty favourably with the rest of Western Europe, and certainly better than certainly countries in Eastern Europe, for example. So another factor which has perhaps influenced the climate in the run-up to Grenfell was what's the word I'm looking for? Building control has been deregulated since about 1985 with NHBC, and approved inspectors since 1997. That's brought competition into building control, with developers essentially being able to choose who approves their building. And some would certainly argue that's been a factor in how standards have changed. Personally, I'm not so sure how much of a factor it is, but it's certainly been raised by some. Another factor covered on the next slide, please, is the use of combustible foam insulation, which Jim touched on, typically phenolic foam or PIR foams. They've been used for perfectly good reasons. Principally, they perform a lot better than the non-combustible alternatives, such as mineral wool. So you need less of a thickness of foam to achieve the same performance, which means a developer will get a bigger flat for on their plot size. But they're also easier to work with and lighter. So there are significant advantages in using them, at least from a non-fire point of view. So if we go back to the fundamentals, this is the requirement we're looking to achieve of external walls. This is the building regulations requirement. It's, as you can see, fairly short and sweet. The requirement is that the external walls should adequately resist the spread of fire. What that means, it isn't defined. Certainly for low-rise buildings, there is no specific guidance unless you're unless you're very close to a site boundary. For what are known as high-rise buildings with a floor over 18 metres in the UK, or England at least, there are two options given in the guidance. One is to use limited combustibility materials, which would essentially materials which don't contain large combustible content and that don't burn very well. I appreciate there's going to be a big debate in the Grenfell inquiry as to whether the guidance actually covered ACM cladding adequately, but we're not going to get into that here. The other option given in the guidance is for the whole wall assembly to meet the performance criteria given in BR 135 using full-scale test data. Now this grew out of some essentially back then, there were essentially ad hoc tests carried out at the BRE back in the late 80s, and this led to the development of the BS 8414 test and the BR 135 guidance, which is the only measure of fire spread which kind of relates back to that building regulations requirement and defines what is an acceptable rate of fire spread. Jim's going to talk. Art is going to talk more about the fire testing in detail and what these ad hoc tests have evolved into in the next section. We have the next slide, please. So Grenfell Tower, I mean, Jim talked about it. It's obviously going to change things enormously in terms of the approach to fire safety, the whole regulatory system, and the guidance applicable to buildings in England and Wales. And beyond. Can I have the next slide, please? So the government response has been multi-stranded, as you'd expect with such a major disaster. Initially, it's focused on testing of wall systems with ACM cladding. There's then been a series of advice notes issued principally during 2019, but with a summary of all of those advice notes issued earlier this year. The public inquiry is ongoing and is currently in phase 2. There's been the Hackett review of the building regulations and fire safety, essentially a review of the system. And the key conclusion of that was that the system, the construction industry is deeply flawed and it needs a radical overhaul. There have been amendments to building regulations. Combustible materials have been banned in external walls of residential buildings with a floor more than 18 metres above ground. And the guidance has also been amended to require sprinklers in blocks of flats with a top floor above more than 11 metres above ground. That's down significantly from 30 metres. There is a wider technical review of approved document B in the offing, but timescales for that are a little unclear at the moment, and it's going to have a very wide scope, so it might involve research and, as I say, it could take a while. The draft fire safety bill was issued last week, and that's the government's response to Hackett, which I'll touch on more in a few slides. We can have the next slide, please. So the government initially tested a range of ACM panels from buildings in small-scale tests. There are 3 categories. One is limited combustibility. Category 2 involves panels where the PE core has been treated to provide some degree of fire retardancy. And category 3 is where the PE core is unmodified, i.e. no fire retardancy whatsoever. And the government tests showed that the vast majority of buildings used the unmodified PE core ACM. There was a proportion, less than 20%, with used ACM with some degree of fire retardancy, but there was no use of the limited combustibility ACM. And that's also been reflected on other studies, as shown on the next slide. Again, this is showing the vast majority of ACM actually uses unmodified polyethylene cores, and that's in conjunction with all types of insulation. Again, up to about 20% of ACM in use is fire retardant to some degree, but little or no use of the limited combustibility ACM. And the ACM has been in use on all sorts of buildings, from social housing, private dwellings, and also significantly on student residential buildings. The government then moved on to some full-scale tests based on the BS 8414 criteria. Art is going to talk about these in a bit more shortly, so I won't dwell on it, but the key conclusion was that unmodified polyethylene ACM was a problem irrespective of the insulation material it was used with. Fire retardant polyethylene was probably inadequate if used with combustible foam insulations, but might be adequate if used in conjunction with stone wool insulation. The focus then moved to some degree from ACM to systems that don't incorporate ACM. As I mentioned, the government issued a series of advice notes. This is probably the most notorious. Advice note 14, it's essentially a decision tree. And the first question it asks you is, are the materials, including the panels and insulation, of limited combustibility? If the answer is yes, you end up in the left-hand green box, which is good. If the answer is no, the secondary question is, has the system been tested to BS 8414 and achieved the BR 135 criteria? If the answer is yes, you end up in the right-hand green box, which again is a good result. But the problem was the vast majority of buildings, or at least certainly a large proportion of buildings, there isn't a yes answer to either of those questions, so they end up in the red box, where the advice is to seek professional advice and consider remediation. And this provoked problems with mortgage lending. Mortgage lenders got wind to the issue, and the fact that they could be lending on money on dwellings, on flats, which for which significant remediation works could be required to the block in which the flats are located. Another factor which has been affecting the climate has been fires. Since Grenfell, there's obviously been a lot more media attention on building fires than would otherwise have been the case. But these two probably would have made the news even prior to Grenfell. On the left-hand side, that's Samuel Garside House in Barking, where there was a major fire involving timber cladding and timber balcony materials. The right-hand side is the Cube in Bolton that Jim mentioned. Both these buildings were under the 18-metre threshold, and there were no fatalities. But the fact there were no fatalities may have been a function of the time when the fires occurred, i.e., in early evening rather than later in the evening when more people would have been sleeping. So the concerns with respect to lower buildings have been reflected in government advice. For example, this extract from the advice note in January has made the point that people carrying out assessments of external walls need to consider that building regulations requirement that I referenced earlier on. So even where the appropriate guidance, being approved document B, doesn't actually give you any guidance as to what's appropriate, the government are saying designers, assessors need to consider the fundamental building regulations requirement. The draft building safety bill was published last Monday, and this is the government's response to Hackett, and that's obviously affecting the climate to some extent. It's probably best part of 4 years. Seems to be the best estimate as to when this is going to come in. But people are aware that big changes are in the offing. We can move on to the next slide. I've summarised the key changes. There will be a new national regulator for high-rise residential buildings initially. Initially, the scope will be 18 metres or 6 stories. But the scope may extend in the future. It may cover other types of buildings beyond residential. With respect to existing buildings and external walls, the key requirement is that building owners will need to develop a safety case to go to the regulator for approval. Exactly what this will mean in practice is not 100% clear yet. But I think what we can safely say is that the regulator is going to be very interested in the fire performance of external walls. So I think the point I'm trying to make is that anything we do now with respect to external wall assessments ought to bear this in mind. as it's something that's in the offing and coming down the line, even if it may be 4 or so years before that happens. So I'm going to hand over to Art now, who's going to talk about testing.
Thank you, Ben. What I'd like to do is just spend a couple minutes and talk a little bit about fire testing and the way we use that in terms of trying to meet the regulations. As Ben just indicated a minute ago, the regulations state that the external walls of buildings shall adequately resist the spread of fire over the walls. Next slide, please. So there's a couple of options that we can meet those regulations. The first option is we can utilize limited or non-combustible materials, and it's quite obvious that if the materials won't burn, then we will meet the regulations to demonstrate that we adequately resist the spread of fire over the wall. The most common method for demonstrating compliance with the regulations is to conduct large-scale testing, which qualifies the assembly, the exterior wall assembly. Another option, which is not really favorable at this point in time, is to conduct a desktop study. It needs to be conducted by a qualified specialist, and the performance criteria of BR 135, which utilizes testing in accordance with BS 8414 as the test data, is the basis for any of these evaluations. Another option is to conduct a holistic fire engineering approach to determine how the material will perform, or how the assembly will perform. But any approach that's taken needs to have some form of large-scale fire test data which demonstrates the fire performance of that assembly, and it does meet the qualifications of the applicable regulations. Next slide, please. So when we conduct large-scale fire tests, the key component is this is a test of the exterior wall assembly. It's the entire assembly itself. It's not material tests. And what we're looking at are the different materials that are being installed in that assembly, as well as the installation techniques. The assemblies are subjected to a realistic fire exposure conditions. These are not bench scale or laboratory scale sized or exposure type tests. These are very large fire exposures conducted in carefully controlled laboratory conditions, which allows for very good repeatability of test results so that we can allow for a comparison between assemblies because we know that all of them have been conducted and tested and evaluated in the same manner. The testing, and I'll get into a little bit more of the details of the assembly later on, but it's a basically a visual monitoring of the flame spread up the exterior face of the wall assembly, as well as we're monitoring temperatures within the core of the assembly and on that external face as well. This is a pass-fail test. This is not a graded test. One sample is not judged to be better than the other. One assembly is not judged to be better than the other. It's either they pass and meet the requirements or they do not meet the requirements. In particular, the BS 8414 test is a large-scale test. There's two parts to it. Part one has a masonry backup wall, base wall, which I'll talk about in a minute, and part two uses a structural steel wall. This is more realistic or representative of how the actual construction is will occur. And again, we're looking at flame propagation mainly over the exterior wall surface. We don't want to see fire spreading up the vertical face of the assembly, but we also don't want to have fire burning within the interior in the combustible core within the wall, because that just it leads to issues with the fire brigade for extinguishment. This is a 30-minute fire test, so as long as we get 30 minutes of acceptable fire performance, that's been deemed acceptable by the regulations. And there also is a mechanical performance consideration part of the test, which is to evaluate, does the material stay in place? Do we see any further ignition or burning or charring of the material? Do we see melting and dripping? Some of those characteristics that we mentioned earlier that can lead to spread of fire. The apparatus is a large apparatus. It's multi-story. It's 8 meters high by 2.5 meters, 2.6 meters wide. And we incorporate a 1.5 meter wing wall to create a re-entrant corner, which increases the burning of the sample face because of re-radiation from that re-entrant corner, that exterior wing wall. The fire source is a 550-pound wood crib, which simulates the fire source down low from a lower floor and impinging up on the face of the wall. In this test, we are looking at the spread of fire over the exterior face of the wall. What we're not looking at is evaluating any type of interior perimeter fire barrier type system that will prevent the spread of fire interior from floor to floor. So this is only an exterior test of the assembly. Next slide. So this is a little schematic, a side schematic of this. Again, this is an assembly test, and I want to reiterate this again and again and again. We are not evaluating components. We are not evaluating systems. We're not evaluating products. What we're evaluating is the constructed assembly, which includes the insulation materials, whatever that exterior cladding material may be, and the attachment system. How is it all constructed? Again, the fire is simulating an interior fire that transitions to a post flashover fire with the fire plume exiting out a window opening or a door opening. And the flames can either, by virtue of how we construct the assembly, wall assembly, and run the test, the flames can either enter the exterior wall cavity, or they can come up over the face of the wall and burn up the exterior face. And again, we're monitoring vertical exterior flame spread, either vertically inside the core or on the exterior face. Next slide, please. BS 8414 is one of many tests. There are numerous tests internationally that have been developed to evaluate essentially the same principle: exterior flame spread on exterior walls containing combustible materials. NFPA 285 is used in the United States. CAN ULCS 134 is used in Canada. We have other ISO standards, DIN standards, and the Australian standard. Everybody has, or not everybody, but there are a number of exterior wall, large-scale fire tests, which are similar in concept. But the issue is they're very different in terms of the fire exposure conditions, the requirements on how you construct the assembly and run the test, and what that performance criteria is. So because they're all slightly different, we can't use one test to demonstrate performance for another test, but they are all similar in concept. And what we're looking at is, this is a schematic to show you that we're looking at the exterior base wall assembly, or I'm sorry, let's start from the outside. So we're looking at the cladding materials, whether they may be the ACM material or an HPL or some other combustible material. Looking at any interior insulation materials, whether they be combustible or non-combustible. If there's a combustible water-resistant barrier material inside there for the building envelope, that is considered as part of the assembly. And then the base wall assembly, whether it be the masonry assembly or a steel stud and gypsum wall assembly. Other components that are included in there may be cavity barriers, anything that might be done at the header at openings to protect that area to prevent fire from getting up into that air cavity space. We may be evaluating the attachment system. And one of the other components that we do incorporate into this is actually the air cavity space, because that plays a key role in how that fire may spread vertically, either interior or on the exterior of the assembly. Next slide, Alex, please. So large-scale testing has many uses. It can be used for research and development, for the development of different products or different assemblies, but usually it's used for qualification testing. A manufacturer will have an assembly, have a product that they want to use in an assembly, and they'll go out and test that for qualification. The large-scale testing can also be used for post-fire forensic testing. So for instance, after Grenfell Tower, BRE ran a number of tests to try and understand what happened. In test 1, they used one of the category 3, the unmodified ACM cladding materials, over a PIR insulation. The results of that test showed that the flames extended over the top of the apparatus very quickly. So then scientifically, what we did is we changed out the insulation material, the combustible PIR, with a non-combustible or limited combustible stone wool insulation. But the flames still extended up over the top of the wall assembly very quickly. So at this point, it looks like you're going to point towards the cladding material as being the culprit in this. So they changed out the ACM material from an unmodified PE ACM to one that has some fire retardant in it, category 2 ACM, back with the PIR insulation. And that assembly failed with flames over the top of the apparatus 25 minutes into the test, so very close to the end. Now that could be an issue with how it was constructed in terms of air gaps, air cavity spaces, attachment systems, things like that. So that could be investigated further to try and come up with a system with those components to see if it can work. The fourth test, or one of the test 4, was run with the ACM material with the fire retardant core and a stone wool insulation, and that passed. So by methodically working our way through different variations of the exterior wall assembly, we were able to evaluate the performance. Small scale testing can also be used in evaluating exterior wall assemblies. The small scale test can be used to evaluate the component combustibility And if the components are deemed to be limited or non-combustible, then you're complying with the regulations and there is no need for a large-scale fire test. So we do allow some component testing, but only when we say if they're all non-combustible. And that makes sense because if I have materials that don't burn, I don't have a fire hazard. The other thing that these small scale tests will do is they provide a lot of fundamental material burning characteristic data, such as the heat release rate and the total heat release that was talked about earlier. We can also look at the time to ignition, how quickly do the materials ignite. We can determine what the heat of combustion is, the amount of energy contained per unit mass of that material, and get a feel for where does that material lie in terms of how much potential can it contribute. We use this a lot of times to rank order materials and try and understand which material is better or worse than another material to understand what that implication may be in the large scale testing. Small scale testing can also give us a little bit of information on the material fire performance characteristics of that specific product in terms of melting or dripping or flowing or pooling, so we can understand based on the type of material, how does it perform. Next slide, please. So again, large-scale fire tests are assembly tests. We're looking at the entire assembly, and minor changes to the assembly may have significant outcome on the performance of that assembly. But the one thing is that fire testing is deemed to be providing definitive answers to the actual fire performance of that assembly. And usually because we trust these large-scale fire tests, they are almost always accepted as proof that this assembly does or does not meet the requirements. The issue becomes that running a large-scale test is very cost prohibitive. And it's very difficult, if not impossible, for manufacturers to evaluate all possible exterior wall configurations. So this is where the idea of the desktop studies come into play, because they can effectively be used to justify deviations to qualified test assemblies, as long as those are within certain bounds and certain known restrictions. Desktop evaluations rely on the experience of the evaluator and the judgment, so they're subjective. So they aren't as definitively accepted as a large-scale fire test will be. So it has to be a qualified specialist doing this work. The other issue is the quality of the input and the experience of the evaluator is directly linked to the quality of the desktop study. So it's just like a computer model, data in, data out. If you have good information going in, you're going to get a better quality desktop study. So at this point, I'd like to turn it back over to Ben for a little bit of remediation and EWS.
Thanks, Art. Okay, so I think where I left off was with the issues with mortgage lending with flats in blocks with cladding issues. So the EWS1 form was intended to address that issue. The idea is that it would provide a consistent and structured manner to carry out assessments, which would enable assessors to state that the building had been looked at and it was adequate, or the external walls were adequate. I touched on earlier the issues with buildings under 18 metres, and I've highlighted that there. It wasn't really intended for buildings under the 18-metre threshold, but in practice we're finding that EWS1 forms are being asked for buildings up below that threshold. So it gives you two basic options. One is option A, where the primary materials in the wall are unlikely to support combustion. So if you've got limited combustibility materials, I mean, as Art mentioned, you put them together, you're probably not going to have a problem. Option A1 is I guess the most favoured option, where it's straightforward. You're just looking at a wall. It then gives you two options for buildings with what they call attachments, which typically means balconies. But the reason for that was there might be, if a building has balconies with combustible materials or particularly problematic combustible materials in the balcony, there might be the mortgage lenders might take account of that, because any remediation works needed to the balconies would be, I guess, less extensive than if it involved opening up the external walls. I think we're finding that in practice that the problem still seems to arise if the conclusion of the assessment is that the balconies are a problem but the walls are okay. The mortgage lenders are still being reluctant to lend on the building. The other option is option B, where there are combustible materials present in the external walls. that tends to be a more involved and extensive assessment. If we can move on to the next slide, please, Alex. The EWS1 form does give fairly clear guidance as to how the assessment should be carried out. It should take account of regulations and guidance, both currently, i.e. new guidance, which has changed significantly, but also that which was current at the time of design and construction. So it's asking you to refer to a clear benchmark. It's not a matter of opinion of the assessor. It does need to be benchmarked against published guidance. So the approach we've been adopting in JGA has been to, first of all, review the documentation, then carry out inspections on site to confirm materials and that cavity barriers are where they should be and installed correctly, and take account of any particular issues associated with attachments such as balconies and risks that the geometry might represent in terms of fire spread to or from balconies. We've taken the view that a detailed report describing the assessment is essential, particularly given the changes in the regulatory system that are coming down the line under the new fire safety bill. We don't see it as adequate simply to sign the form. So for systems with combustible materials, one option is obviously remediation works to remove the combustible materials, but it can be possible to support a B1 conclusion, which is the other positive conclusion given on the form. So that might be based on existing BS 8414 testing and system certification. It might be based on a desktop study carried out at the time of design and construction, provided that desktop study was suitably robust. Another option is new 8414 testing of the as-built wall system. A new desktop study is in principle possible. There is a recently published BS 9414, which gives guidance on how to carry out desktop studies. Now, no doubt, because of the poor reputation that desktop studies have, it's extremely prescriptive and probably quite conservative. So in practice, we've not, to date at least, we've not found an opportunity to apply it. It requires a great deal of test data of very similar wall systems, which in practice doesn't tend to be available. So common findings are, a common one is no records explaining the justification for the use of the materials. Equally common, I guess, in our experience is that there might be records indicating that building control were consulted and agreed the use of the materials, but there's no technical evidence explaining the basis for that decision. We're finding a lot of complex facades with multiple wall systems, some of which might have suitable justification, some which don't. Another common finding is that there is test data or a desktop study available, but the wall build-up, the wall system, doesn't match that. The next slide shows an example of that. BS 8414 tests are typically carried out with barriers around the hearth opening where the fire is located. And the hearth opening is intended to represent fire breaking out of a window. Guidance recommends cavity barriers. Sorry, Alex, if we go back one. Guidance recommends cavity barriers are provided around windows, but we occasionally find buildings where that's not been done, i.e. they've been omitted and only provided at slab level and party wall level. However, if the system has been tested, assuming cavity barriers around the hearth opening, then the system, the as-built building should include cavity barriers in those locations. Next slide, please. We occasionally find cavity barriers are not installed in line with manufacturer's instructions, usually the wrong way round or with excessive gaps. Occasionally find gaps at junctions between cavity barriers or gaps where the cladding support rails penetrate the cavity barriers. So cavity barriers tend to be a big issue. So approaches to resolving issues, as I touched on before, removing combustible materials is an option, full-scale testing for the as-built system, modifying the system and carrying out full-scale testing. These three are the common approaches that we're finding. And with that, I'll hand back to Jim to conclude the presentation.
Next slide, please, Alex. So the effect of the EWS1 certificate is that buildings are blighted. The London residential market is going to grind to a halt because either the building doesn't have a certificate or the flat owners cannot get a certificate. Remember that the EWS system was designed to certify whole buildings and not individual flats. So that's resulting in owners who can't sell, buyers not buying, lenders not lending, surveyors putting nil values on properties, an absolute nonsense in my view. And lenders are going to have to write down mortgages. The system is truly broken. Next slide. Ben has outlined the solutions from removing combustible cladding, etc. But some of the other solutions involve recognizing that the building regulations are about life safety and not property safety. And so you could adopt the Scottish solution, which is building-wide evacuation if a fire spreads to more than 2 compartments by improving the alarm system. And sprinklers, of course, are an option to be considered, and it's encouraging that the English regulations now look to install sprinklers on buildings over 11 meters in height. Next slide. So the owner's response has been, who can we sue? Can we claim on our building insurance or our NHBC certificate? How can we pursue our loss? And they come to companies like JGA and ourselves saying, can you do a building-wide assessment on our building? The owners have lots of targets. Next slide. They've got an insurance policy that they may be able to claim on. They have a contract with a developer. The developer has engaged a designer, architect, specifier. There's a certifier involved, a contractor, a facade contractor, even, dare I say it, a fire engineer, chartered surveyor, and ultimately the lenders who have approved the lending on the building. Next slide. This is a diagram from the Guardian newspaper on Grenfell. It's illuminating because it shows the complex relationships in the construction of high-rise residential buildings and in their overcladding. Next slide. So how can we help? Well, we recognize that we can't be on the side of angels every time, and sometimes we have to defend the indefensible as best we can. But these are complex issues, and that means that the fault is rarely down to one single material company or individual. And a proper perspective on liability that we can bring from our knowledge of the construction industry and of fire safety engineering means that we can bring and illuminate liability. It also means that we can utilize alternative strategies in order to minimize costs when non-compliant buildings have to be brought in compliance with current government guidelines. Next slide. So I hope this has been informative for you. Danny is going to host a question and answer session, and I'll hand over to her now.
Hi, everyone. Okay, thank you so much to our experts. We did have a couple of questions come through the chat during the webinar. So I will look at those and ask those while we get everyone else to submit their questions. And just as a reminder, if we're unable to get to your question, we will do our best to follow up individually to answer. Okay, so will desktop studies continue to be accepted or withdrawn due to the perceived risk? And I'll open it up to our panel.
Shall I have a go at that one? I think in the UK at the moment the environment is extremely conservative. For new build, at least in England, they're not an option. New build high rise anyway. The requirement is to use non-combustible materials. For existing residential buildings with combustible cladding materials or insulation materials, I think that they are an option. But as I touched on during the presentation, there is a new BS which has been published, which I guess provides the obvious route to carry out a desktop study. But it is extremely prescriptive and conservative. So in practice, I don't see it happening a great deal, at least in the short term.
There's a further complication with this, which is that it needs to be, these studies need to be done with both information and by competent chartered engineers who have to be insured. And the cost of insurance, particularly of professional indemnity insurance, is rising. And also, there are really only 2 test houses in the UK that have got the database upon which chartered engineers would need to rely with respect to fire testing of materials. And they are Elements and Warrington Fire and the BRE. And their data is confidential to the clients for whom they've tested the materials.
Okay, thank you. Another one, if installations are clearly non-compliant with building regulations, can alternative methodologies like sprinklers or alarms be used rather than large-scale remediation?
Well, my view of that is yes, they can, but you're then going to have to get that past the building safety regulator in the health and safety executive to come. And certainly the experience in other industries that have been regulated by the HSE is that they take a very prescriptive approach. So, for example, the cost of providing a safety case on an offshore installation is enormous.
Okay. Will companies be expected to include items within the recently issued bill that are currently being constructed?
I think the answer to that is no. The bill doesn't include technical guidance as to how to build a building. It's how the regulatory system will be structured. I mean, there are aspects that have been raised during the Grenfell inquiry and are likely to come in at some stage to UK building regulations. I think the 2 most notable are the alarm system, which would enable fire brigades to evacuate high-rise residential buildings on a floor-by-floor basis by hitting a button, and also provisions for escape for the mobility impaired. So that might mean an additional lift designed for firefighting and evacuation. Probably not an additional lift in total, but having maybe 2 lifts within the building designed for that purpose. But the bill itself doesn't include technical requirements. So at the moment, to some degree, it's speculation as to what is likely to come in the future.
Great, thank you. Another question, this one I think maybe for Art, do you see the necessity for larger full-scale fire tests, not just incorporating vertical, but horizontal spread? Also, window openings need to be incorporated in such larger tests to allow the understanding of the window and cumulative aperture effect of such a test. It's a bit of a statement combination question.
Yeah, I think all of the large-scale fire tests that are available internationally do look at vertical fire spread is the key issue that we're looking at, but we also do look at vertical or lateral spread of fire, especially in the NFPA 285 standard that we use in the United States. That is one of the key components. And then also the ability for the assembly. You're looking at the assembly and how it's going to react. So I think it may be the components such as how you construct the header openings for windows and for doors is going to be a key component. It is touched on in the BS 8414 with cavity barriers, as Ben indicated. They are typically tested with those cavity barriers for that sole purpose. I think the tests are in general good. I think the issue lies on it's not being constructed in a manner that's consistent with what was tested. So that becomes the issue. The testing is pretty good, but the construction and the inspections need to be improved such that we ensure that we're building what we actually tested.
Okay, thank you. Another one, will companies be expected to include items within the recently issued bill that are currently under construction?
I think we had that one, Alex. Was that the one I?
Oh, sorry. Okay. I have many, so sorry. Are building owners inspecting brick, masonry, and cavity walls when considering different wall types?
The short answer to that is yes. It's probably not top of the priority list, but I guess part of one of the criticisms perhaps of the government's response to post-Grenfell is that it's been left to industry to prioritise their response. So there are a lot of buildings with brick facades but have combustible insulation, and may or may not have complied with the guidance at the time of construction, i.e. may not have had a suitable BS 8414 test carried out or suitable desktop study. In terms of risk, they're probably at the lower end of the scale, but certainly responsible building owners are looking at buildings with brick facades but combustible insulation.
Is there an equivalent EWS one for commercial buildings?
Not that I'm aware of.
No, I've not heard of anything along those lines either.
Okay.
That's not to say that people aren't looking at it. I mean, I think with commercial buildings, we're increasingly being approached by buyers on the cusp of buying a building and want the external walls checked out. So there might not be a structured way of looking at it, but it is something building owners or people looking to buy a building are certainly interested in.
Okay. All right, we'll do one more question before we end the webinar. How likely do the panel think that the same level of interrogation of fire in buildings under 18 meters will take place following the exercise for all residential buildings over 18 meters?
Well, my experience is that it's already happening. Well, I've got developer clients who are looking at what they did on their low-rise developments, up to 5 stories.
Okay. All right, well, thank you, everyone. I just wanted to be respectful of everyone's time, so we'll end the webinar here. Thank you all so much for taking the time out of your day to join us. We really appreciate it. We hope that you found it helpful and informative. So please, everyone, take care and stay safe. And we will look at the questions and answer. So look out for that. Thank you, everyone.